lecture.
All right, well, thanks. And thanks to the organizers for asking me to be here. So I guess Mark wrapped up saying he didn't want to deal with the hard things, so I'm going to deal with the hard things maybe. Which I guess the first hard thing is figuring out how the microphone works. All right. So I'd like to tell you about community structure. And you should think of this as empirical results, so sort of facts about the world in the sense that, proteins are made of alpha helices or whatnot. There's particular tools, and basically we had to invent the tools. And I'll give you a hint as to what some of those tools are. And if you're interested in the tools, we can talk a little bit more offline. And I think actually the development of those tools in more general settings is of a lot of interest. And so I was at Yahoo some number of years ago, and I was the resident matrix expert. And there was two different business units that came to us that had two particular problems that at the end of the day boiled down to finding good clusters or communities. And it turned out that the matrix methods didn't work particularly well, and manifold methods, which are popular in machine learning, didn't work well, and a whole range of other sort of data analysis tools actually failed rather egregiously at providing even qualitative insight into what these sorts of graphs look like. And so we had to take a step back and invent some tools. And at the end of the day, what the tools are is we had to use algorithms for intractable problems. So approximation algorithms for intractable problems to sort of poke at the data in order to try and answer questions about what the data might look like. So I'd like to tell you roughly sort of what the data might look like. And the first sort of word of warning is sort of whatever ideas you have in the back of your mind or hypotheses you might have about ways that the data might look nice or reasonable or whatever are probably wrong. I mean, these graphs are pretty nasty beasts. And that applies for a fairly wide range of large social and information networks that arise in a fairly wide range of applications. And I'll give you some examples in a little bit. So the first thing to note is that there's sort of lots and lots of data out there. And if you were doing large-scale data analysis, so I'd like to take a very data approach in a sense to this. If you were doing large-scale data analysis maybe 20 years ago, you're probably sitting in a physics department working in high-energy physics or astronomy or something. Some of the matrix algorithms I actually mentioned we applied to DNA SNP data, hyperspectral image data maybe, and then a lot of sort of other data sets, term document data, collaborations, citation networks, internet networks, web graphs, advertiser bitted phrase graphs. I'll mention what I mean by that. And what you should note as you sort of go down the page here is that whereas in a lot of sort of scientific applications up here, you might know a lot about where the data come from. So you might not have a statistical model, or you might, but you might not have a statistical model in the sense of you write down Bayesian priors or whatever. You really know a lot about where the data come from. When a star explodes, you know that the star, unless it's right next to a black hole, sits in three-dimensional space, something about the energy spectrum and so on and so forth. Whereas, an advertiser bidded phrase graph, why does a given advertiser bid on a phrase? He might be doing it because he's interested. He might be doing it because he's not interested, but he wants to send some false signal to a competitor. He might be doing it because it was a mistake and he couldn't figure out how the system would work. I mean, why do you click on a given web page? All the same sort of things would hold. And so what we'd be able to say about these sorts of data sets is in some sense much weaker. You should think of these as extremely large, but also extremely sparse. So there's going to be a priority on algorithmic tractability, but also statistical modeling. But the statistical modeling you're going to be able to make is a lot weaker, maybe in some sense, that you could in previous applications. So networks are sort of the topic of the day, and a lot of the data sets I had on the previous page can be thought about or modeled as networks. Technological networks, biological networks, social networks, information networks. I'm going to sort of lump these together. You should think of these as a little bit different, but maybe something from LinkedIn or LiveJournal, collaboration graphs. A lot of these are publicly available, a lot are not. Information networks, maybe some proxy for the way information moves around. So co-citation, blog cross-postings, advertiser bidded phrase graphs. And looks like I'm going to have some problem with the coloring a little bit. So I'll try and point out there should be various sort of gray scales to indicate there's sort of a boundary and a core and so on some other levels. We're going to model these things with graphs. The nodes will represent some sort of entities, and the edges will represent some sort of relationships between the entities. And we're going to ignore direction. Some of what I say will apply to directed graphs and some won't. That's actually an important topic for future work. We're going to ignore directedness, which for community applications may be less important, but for a lot of applications will matter a lot. Weightedness doesn't matter. You can weight it in any sort of reasonable way. And what I'm going to be talking about is empirical claims about the world. You can certainly come up with graphs that will violate the particular conclusions we're drawing, but a wide range of ways people pre-process graphs. will satisfy this. So something that you should keep in the back of your mind is maybe different approaches that people can take to these networks, but also to data much more generally, and to sort of focus on maybe two high-level streams. I want to mention sort of if you're a computer scientist, you probably think of the data as a record of everything that happened, every transaction that happened at Walmart in the last month. And the goal is to process the data to find interesting patterns. And usually the things you want to find are intractable, either in general in the models of data access that are appropriate for the size of the data. So what you want to do is develop some sort of approximation algorithms for different models of data access. A very different view of the world, and it really is very different, is the way maybe a statistician or a natural scientist would think about the data, where the data really are just a particular random instantiation of some underlying process describing patterns in the world. And the data are so holy because it's the only access you have to the world. And the goal is to extract some information about the world. And so you try and make inferences about unseen events by positing a model. All right, so now if you're at an internet company and your goal is to do something personalized, to predict whether a given user at a given web page at a given time of day who's sitting in a given zip code, and maybe you have personalization who clicked on a given page an hour ago, is going to click on this particular advertisement or this particular link, that thing's not even going to be a high-frequency event. That thing's not even going to exist in your database. And so you need to have some sort of statistical model, but the scale of the data you're getting to giga and tera and petabyte scale is such that you need to worry about algorithmic issues. So these are certainly not going to be incompatible. So as you may know, sort of statistical and probabilistic ideas are central to a lot of recent work on developing randomized algorithms for matrix problems. That was the sort of thing that I was working on when this line of work began. A lot of intractable optimization problems on graphs or networks will yield some sort of approximation when you make assumption about the network participants, submodularity or convexity sort of assumptions. Boosting is a statistical technique in which the computational parameter, let's say the number of iterations, you can also think of as a regularization or smoothing parameter. So there's a real interplay here. They're very different views of the world, but we're going to be exploiting the interplay. And as I said, the reason we're going to be thinking about the interplay is that we're going to want to be using worst-case algorithms. Those are our tools. We're going to be wanting to use worst-case algorithms. But we really don't care about the particular thing that those worst-case algorithms compute. We want to infer properties about the output of those worst-case algorithms based on the implicit geometric and statistical steps that those algorithms make. So again, the coloring's a little bit off here. But to give you an idea of an application where this arose, and this is an example of an application that's a large consumer of these sort of network techniques. So sponsored search. So sponsored search is basically text-based ads driven by user queries. So you go to a search engine, you enter something into the search box, which because of the colors, I guess, is here. And you might think that the most important thing is 1, 2, 3, the top 10 results. At the user end, you might think that really that's far, far from the most important thing. The most important thing is these guys here and these guys here, which are advertisements. This is what pays the bill. And so a lot of work goes into doing a good job. Now, there's a lot of natural language issues. There's a lot of sort of economic and algorithmic issues in terms of how to structure those auctions. From the point of what we want to talk about today, I'm going to gloss over those. From the point of what we want to talk about today, let's try and construct a graph, and then we might want to try and extract some sort of clustering structure. So let's construct an advertiser keyword graph. Discretization of the advertisers on one side, discretization of the universe of keywords on the other side, and let's say a link between an advertiser and a keyword if the advertiser bids on that keyword or clicks on it or whatever. So now you have a bipartite graph. It could be weighted. There's lots of other ways you can process this. And the goal is to mine this thing in a data analysis or data mining sense in order to provide new advertisements, let's say to maximize click-through rate or return on investment or whatever. And so you might be interested in clustering or community-related problems in these sorts of graphs because let's say you want to do something called marketplace depth broadening. You want to find new advertisers for a particular query or submarket. Query recommender systems suggest to advertisers new queries. Contextual broadening, broaden a given query using other sorts of information. So these are the sorts of things that have the flavor of recommendation systems, but the details will be very different. So as I said, two particular business units came to us, and they had exactly these problems. So one wanted to do query broadening, and you might think intuitively if you're in the middle of a sort of a concept class, you can expand to nearby queries. Maybe you're in the middle of a cluster, a community, whatever that means. You might expand the nearby queries and get something meaningful. Whereas if you're in a very messy part of the graph, that might not be so possible. And the other group wanted to pull out sets of nodes that it could basically think of as an economic market to do bucket testing on. Right? So you pull out a set of nodes and you make things a little bit bolder, or you do some sort of test on them, which is a very common thing. So The goal in both of these cases is to find isolated, in some sense of the word, markets or clusters with, let's say, sufficiently money or clicks and sufficient coherence. So such that it's worthwhile, it's big enough, sufficient coherence that you can pull it out and think about it as a market, as an economic entity. What's usually not asked, is this even possible? Right? I mean, the usual MO is to define some objective, and if you get a good result at the end of the day, you write a paper, you push it into production, and if you don't get a good result at the end of the day, it's not clear what to do. So it's not even asked whether this is possible. So some of the tools we developed to actually be able to answer the question, is this even possible? Namely, it'll be able to address the hypothesis that the world looks nice in some sense. And so one sense in which the world might be nice is that you have, let's say, the gambling market of keywords and advertisers, which is one that's of interest because it's, as you imagine, high revenue, and maybe a sports market. And you want to say, I want to get the intersection, sports gambling, and I want to pull those out to do bucket testing on. So the fact that you can draw this thing on the piece of paper and draw a boundary around gambling and a boundary around sports is a very strong statement, right? I mean, basically it's saying that you think that k-means or something like that's right. You can put it on 2 or 3 dimensions, and you can draw a nice boundary between it and the rest of the world, and that there's some sort of intersection here. And so it's an empirical question whether the data actually looks like that, right? It's an empirical question whether that intuition's right. So here's what the data actually look like. So sort of a mess. And the most significant thing about this picture, I think, is, as I like to say, I mean, if you know the state of the art in visualization algorithms, you could probably use these sorts of artifactual features to tell me what visualization algorithm we use to plot this graph. Right? This is a publicly available graph. If you knew the publicly available graphs, you probably would be very hard-pressed to tell me what this graph was. Right? So the state of the art in visualization algorithms is that it reveals more about the inner workings of the algorithm than about the graph. Now, that's a little disconcerting, of course. But on the other hand, I mean, take a step back and say, we have this messy thing that we can't visualize. Can we use that to our advantage? Maybe can we use the artifactual properties of that visualization algorithm to reveal some insight about the graph? Or maybe more generally, can we use the artifactual workings of some other sort of approximation algorithm to try and reveal insight into the graph? So that's what we'll be doing. But as you know, there's lots of hierarchical models and core periphery models, small world models, heavy tail models, lots of models that people develop in order to try and provide some insight into what these data sets might look like. And the usual way that you go about this is to ask questions like, what are degree distributions, clustering coefficients? So you ask about degree distributions because that captures some information about the very local scale structure. Maybe there's a very significant heterogeneity locally, captured most simply by a univariate statistic like the degree distributions. Or maybe there's some sort of local clustering. Probably there's a triangles close or something like that. So very local statistics or very global statistics. Are there natural clusters or communities? I mean, what is a cluster? What is a community? Right? I mean, this is a little bit more subtle thing. How do these networks grow and evolve with respect to time? How do dynamic processes, search or diffusion, decentralized search or diffusion of information behave on these things? And a lot of people at the end of the day will want to do some sort of classification or regression or ranking or some other sort of machine learning. So we'll be sitting here for the rest of the day. And you've heard in Mark's previous talk and in a number of other talks, I mean, there's a huge range of ways that people try and find communities. If the data are particularly nice in certain senses, and maybe linear or low rank methods are good based on the SVD or PCA or something. Something that's actually very popular in machine learning is to say, well, the world's not linear, but nonlinear manifolds are appropriate. So the particular statistics that we'll be computing actually won't differentiate between these two. So you can actually test the hypothesis as to whether the data sit on some reasonable low-dimensional place, whether it's flat or curved in some way. Lots of sorts of hierarchical methods, top-down or bottom-up or a range of other sorts of things. Lots of graph partitioning sorts of methods where you define some sort of edge counting metric, conduction or expansion or modularity or any range of things, and then sort of optimize. All right? So how should we go about trying to find clusters or communities? So I should pause now and say that I don't actually know what a community is, and I'm not going to tell you. I mean, I know what different groups of people think communities are. I mean, if you talk to sociologists, I think communities are any group of 2 or more people that are useful to sort of think about interactions in the social world or something. If you talk to computer scientists or applied mathematicians, communities are probably just things that satisfy some of this one of these edge counting metrics or the approximation algorithms. So I think that the basic intuition that a lot of this work starts with, and the particular advertiser bidded phrase graphs I've mentioned starts with this intuition, is to say it's just sort of a matter of common experience that communities exist in these graphs, that clusters exist in these graphs. And it may be true on small graphs, but people actually think about million-node graphs and think about trying to find clusters and communities. So in fact, it's not just small graphs that people think about, or much larger ones. They will say it's just a matter of common experience that communities exist in these things. Although communities are not precisely defined, they're usually thought about as sets of nodes with better connections amongst its members than with the rest of the world. So there's some notion that there's something going on in terms of the nature of the connections internally versus the nature of the connections between the community and the rest of the world. So we're going to formalize this in a particular way, and there's going to be pluses and minuses associated with formalizing this way. But we're going to formalize it in a particular way having to do with something called conductance. So conductance is something that computer scientists love because it's a well-defined combinatorial thing that you can optimize. So the conductance of a set of nodes in a graph is roughly the number of edges crossing between that set and its complement divided by the number of edges inside that set. Not exactly, but roughly it's that. So very much a notion of surface area to volume. If the graph is a discretization of a low-dimensional place, it's exactly that up to lower-order terms, but it's a combinatorially defined thing. So it's the number of edges in the adjacency matrix between the set and its complement divided by some notion of volume. And we want to define, and then the conductance of the graph is the minimum conductance of any set of nodes in the graph. Now, you might think that communities of different size behave in different ways, and relatedly, you might think that algorithms have very non-trivial behavior as a function of size. So we're going to define as something a little bit more refined. We're going to define something that we're going to call the network community profile plot, which is a function of k, the size of the set we're considering, and it's the minimum set of size k and the conductance value of that set. So it's a sort of a size-resolved version of conductance. So just as maybe conductance captures sort of a Gestalt or intuitive notion of cluster and community quality, the profile plot will measure community or cluster as a function of size. So I left out this slide that shows how other objectives behave. We actually looked at a range of other objective functions which capture the internal or the inter or that bi-criteria trade-off. And what I'll be talking about, I mean, I'm not going to be cheating on you here, right? What I'll be talking about will be robust to that particular formalization. And that's the leading order bit. There's a lot of differences between the different objectives, but what I'll be talking about today will be robust to that particular formalization. This is nice because, as we'll see, it's very well understood theoretically and in practice, and so we'll be able to make very strong statements about it in terms of how it behaves. And we'll see that since it's intractable, we're going to have to approximate it. And the state of the art in approximation algorithms is that you filter those through some geometric place. You embed the graph somewhere and you do something. And so at least as important as this particular objective function that we're tying ourselves to is how you approximate it. Right? And so if you don't like conductance, you also have to object later on when I'm doing different sorts of approximation algorithms, because those approximation algorithms, if you have a million node graph with 10 million edges, that's incredibly, incredibly sparse. Those approximation the things you compute will be a function at least as much of the nature of the approximation as this particular objective.
But that's the minimum of all connected subgraphs.
I didn't say connected. So this is going to be important. What we'll see is that if you really beat on the conductance objective, you'll not necessarily get nicer things. And if you demand that it's connected, it'll be trivially connected. Two pieces may be connected by, so that's important. So to say the same thing, how community-like is a set of nodes. We have this conductance, number of edges cut by number of edges inside. I'm going to present a bunch of plots. Small is good. Small means it's a better community by this measure. And we're going to ask for a size-resolved version. So what's the best cluster of 5 nodes? And so you might say, again, I have a problem with color coding, but that should say bad community. So that's a bad community because, you're cutting a lot. You might want to tack those 2 on to make it the 7-node community, but then you're asking a different question. So we want to ask it as a function of size. And maybe that's a bit better community, and that's maybe a bit better one still. I mean, I don't know, but this is the sort of thing that people are thinking about when they're talking about clusters and communities. So we're defining the size-resolved version. Conductance is intractable to compute, so certainly a size-resolved version of it will be. And I've defined this thing, and it might not be obvious what it is. Right? I've defined a combinatorial thing, conductance, and I said we're going to do a size-resolved version of it, and you might be objecting now and saying, I don't even have the foggiest idea what's going on. It's actually a very, very natural thing. All right? So this is Zachary. The previous speaker, Mark Newman, put Zachary up. We embedded it in a slightly different visualization algorithm. This is the network you saw before. And everything's on a log-log plot, which might not matter for Zachary, but when you get to 1 million nodes, that actually will matter. And you see that the profile plot goes down. And you see that local minima correspond to things that you might plausibly want to call a community. More or less any method you apply to Zachary will cut in half there, plus or minus a few nodes at the interface. And I don't know if this 5 nodes is actually a community, but it's certainly more, quote, community-like than if you were to take some arbitrary set of 5 nodes in the graph. So local minima correspond to things you might plausibly want to call a community. So this is I think it's about a 400 node network constructed from Mark Newman from his review article, and I think there's one or two other review articles from the bibliography of that. And what you see is the same sort of thing, that this profile plot goes down and down, and local minima correspond to things that might plausibly be community-like. Now, defining an extremal statistic here, it's fair to ask if what you're seeing is an artifact of that, and it's not. So I'm not going to describe that. But you may ask sort of roughly why is this plot going down? So although I'm computing an extremal statistic, the details, this particular minimum, that particular minimum will change a lot if you tickle a node or an edge somewhere on the graph. The qualitative property of going down is going to be very, very robust. All right? And the reason this thing goes down is because you can put that on a piece of paper and you can look at it and you can tell something meaningful. This thing really is one or two dimensional. There's a left half and a right half, and you cut it in between. Similarly, this thing, you can put it on a piece of paper and look at it in some meaningful sense and glean some information out. So if you look at a discretization of a line, or a discretization of a plane, or a discretization of a three-dimensional space, or a road network, or a power grid, or anything that sort of lives on the Earth, this profile plot goes down. And it's simply because of something, the technical term is isoperimetry. Isoperimetry is a geometric notion that basically says bigger circles are better than smaller circles in terms of their surface area to volume properties. So the metabolic properties of elephants and mice are very different because of the surface area to volume properties. So what this says is a size-resolved version of conductance is just capturing isoperimetry. And if you're living in a low-dimensional place, unless you're going to allow some pathological statistical probability distributions, you're going to go down. And I should note that if you're an expander, this thing is flat. All right? Now, if you know what an expander is, that's good because these graphs are expanders. If you don't know what an expander is, what I'd say is go home tonight. Don't tell me you don't know because I'll probably cringe. Go home tonight and read about expanders, and before you do any more sort of work on networks, at least know what an expander is, because really, expanders are one of the great discoveries in my life. Because if you believe that the data is low dimensional, if you believe that you can put it on a piece of paper, you're making a statement about the way the data embeds in the plane. You might say maybe the data is the plane that is sort of a curved low-dimensional space, or it's some curved surface, which is basically just a curved version of a plane. If you ask yourself, what is the metric or geometric structure that is least like a low-dimensional space, that's an expander. An expander is a graph that has no good cuts, no good clusters. It's a very, very sparse graph. Think of it as like a three regular random graph. So every node has three edges, and it's random otherwise. So very sparse, but very noisy, and there's no good clusters anywhere. These graphs you should think of as being little pockets of structures on top of that. So little bit pockets of structures on top of global noise, rather than a little bit of noise on top of global structure. The expanders will be flat on these plots. So what we've seen is that a downward sloping profile plot is what you see for small social networks that you use for validation, low-dimensional networks that inform intuition, a bunch of hierarchical models that didn't present that, but that are used for various sorts of model building, and very natural interpretation in terms of isoperimetry, modeling data with low-dimensional spaces, k-means. If you're drawing this sort of thing, you're saying that the data looks like k-means. And we noticed in these two advertiser bitted phrase graphs that there was some very sort of striking and very peculiar behavior. And we thought, if this is a real effect, it can't be peculiar to these two networks. So we went back and looked at on the order of 70, by now many publicly available networks. Size scale, think of it as 5,000 to 5 million. If you're getting above 5 million nodes, you probably have more than about 100 million edges, in which case you're going to have problems in terms of the memory footprint about putting it on a single machine. Ideally, you'd like to be applying it to billion node graphs, but then you have to worry about a lot of memory management issues. So the tools we'll be describing are designed, we're not there yet, but are designed to sort of gracefully go to that size scale, because there's a lot of interest in that size scale. But think of it 5,000 to 5 million size scale. When you're below about 5,000, below about 1,000, you put it on a piece of paper and you visualize it. So we're at that intermediate scale. We looked at it on the order of 70. I showed you what these things look like. They're just a mess. So how do you sort of probe them or interrogate them? So we had to develop principal tools to interrogate them. And if we go back to very, very small graphs, we're going to, of course, be consistent with that. So this should give you a sampling of what some of these graphs might look like, a sampling of the types of some of these graphs that we looked at. This isn't a particularly large or small or whatever sample. LiveJournal, ePinions, Flickr, Delicious, co-authorships in physics and computer science, citations, blog cross postings, bunch of snapshots of the web, authors to papers bipartite graphs, a little bit like the advertiser bitted phrase bipartite graphs, various internet graphs. So every one of these is going to be an exception to the simple story that I'll tell you. I mean, you don't have time to go through every one, right? Everyone is going to be an exception to any simple story. the autonomous systems is particularly an exception. I mention that because this has received a lot of attention maybe between 10 and 2 or 3 years ago in the complex networks literature and so on as being an example of a power law random graph. And the reason this is an exception is that it's sort of in some sense designed to be well connected. If you join your service provider and you can't find the rest of the world, you probably go to a different service provider. So at a very high level of resolution, it's sort of designed to be connected. Whereas if you're on LinkedIn or LiveJournal or something and you're linking to some friends, it doesn't particularly matter how that interacts with the rest of the world necessarily. So more or less any other social information graph for which there's not an explicit or implicit connectivity constraint like that will be roughly of the form that I'll be describing. So we had to probe large networks with approximation algorithms. The idea is to use approximation algorithms for the NP-hard graph partitioning problem as experimental probes. So we're going to be using graph partitioning, which Mark just mentioned about before. This is a very classic combinatorial problem. And we're using it not because we necessarily want to partition the graphs, but because it's a tool, and we know a lot about it. And if we're going to be trying to probe million-node graphs that we can't visualize, we want to at least have some control over our tools. And the lay of the land in terms of algorithms for graph partitioning is the following. You can use spectral methods. Spectral methods that you heard about this morning relax the combinatorial problem to a vector problem. All right, normalized cuts will be this. And because it involves computing a vector, which is related to diffusions, think the power method to compute a vector, spectral methods will confuse long paths with deep cuts. So if you have a long stringy thing, the spectral method might inadvertently cut that off and say that's the best cut. Multi-commodity flow. So flow is a totally different method. If your background's in computer science, you probably studied flow a lot and maybe not otherwise, but it's a totally different approximation algorithm, and you're embedding in a totally different place. The steps of the algorithm are totally different. The geometry underlying is totally different. And this will give you a log n approximation. This will be a quadratic approximation, which is a Cheeger thing if you're familiar with that. A log n approximation. And the quadratic actually is achieved on certain graphs. You know, things can be that bad. The log n actually is achieved on certain graphs, and in fact, expanders. All right, so SDP, this is a set of methods that combine these two. METIS is a popular heuristic, a multi-resolution thing for mesh-like graphs. It's actually pretty powerful for tearing apart these graphs also. MQI is a flow-based post-processing, and you can cut and paste these in various ways. Think about these as sort of experimental primitives that we can combine in various ways. To get to million node graphs, we're going to use METIS plus flow. And in a lot of cases, this will give us the best conductance sets, the best communities empirically. It's a fair question to say, are these really things that you want to call communities? But the best conductance sets. And local spectral methods. Local spectral methods are local versions of global spectral methods. And I can talk about that offline if anyone's interested, but it allows us to probe the graph at various places and various size scales. So I'm using these large networks as experimental algorithms to sort of probe them, as I said. And I want you to take that analogy a little bit more seriously rather than less seriously. So think back 50 years ago, you want to ask the question, what does a protein look like? Right? And there are these little things that are nanometers across, and who knows what they look like, right? And so now you see a picture of a protein on the cover of Science or Nature every other week. And roughly the way you answer the question about what a protein looks like is you put the protein in solution or crystal, you send in X-rays or you send in NMR, and you scatter it and measure a whole bunch of junk. And then you look at all this junk, as well as knowledge of the artifactual physics of what you sent in, these various signals, in order to make some statement about what the protein looks like. So we have these graphs that we can't visualize, and we want to know what they look like. So we're going to tear it apart with spectral methods or flow methods and various sorts of combinations, measure all sorts of junk, and then based on all this junk we measured, plus the geometric and statistical properties at various size scales that we sent of the algorithms we sent in, to infer what these graphs look like. So we really don't care about the partitions per se and objective functions value per se. We really want to use these as experimental tools, in a sense. So, what?
You're not using randomized methods too?
So these methods sort of, you run through some steps, you get something, and then you have to round. So randomization appears as a rounding step. Randomization will also appear like the local spectra. We'll choose a bunch of seed nodes and various size scales. So randomization will enter at a bunch of places. That's actually, I had been doing randomized algorithms before, and so if you input a randomization at various places, you can compute not just a single answer, but sort of a whole ensemble of answers. So that's actually, we use that critically in a number of places, yeah. So this will be a typical example of what we find. So this is general relativity. It's about the smallest thing you can find that, so it illustrates the properties of larger size scale. We have 4,000 nodes. Here's a visualization that sort of suggests what you see in the plot. And what you see in the plot is that the community quality by this score, this conductance score, but as I said, any of a wide range of bi criteria that capture internal versus external will behave in the same way roughly, goes down and down at something on the ballpark of 50 to 100 nodes. Over the 70 graphs, I think the mean was 60 and the median was 100, median was 60, mean was 106 or something. So say 50 or 100 nodes, you hit a minimum, and then it gets worse and worse and worse and worse. All right? If your data set looked like a hot dog, you wouldn't see this, because the best cut would be into 50-50. Now, what's going on? So you see that on that graph. You also see that on LiveJournal, and you see that on ePinions, and you'll see that on these four, and you'll see that on 65 other graphs I could show you. So what I want to focus is on the red curves. This is what we get with local spectral methods. And the green curves are flow-based methods. Now, the following will be the case for sets of nodes of size scale 500 to 5,000, say, that spectral methods are, demonstrably and unequivocally worse than flow-based methods. So if your goal really is to find good conductance sets, if you really believe that conductance captures what you want, then there's no point in even touching those. You do a much better job here. Now, I'll show you what these things look like internally in a second, but if that's what you believe, that's the case. Now, more expander-like parts of the graphs, that might not be the case, because diffusions are not particularly discriminative on expanders, whereas for a range of reasons, flow-based methods are more so. And so, it's not necessarily the case that spectra is always worse than flow by the objective function value, but nicer in terms of looking at it internally. So I'll get to that in a minute. And also notice, it's known that the web is pretty compressible, basically because files on one machine might link to files on the same machine. And so, this whole thing is pulled down a couple of orders of magnitude. Remember, we're on a log scale here. A couple of orders of magnitude below, let's say, a much more social type graph with ePinions, whereas once you get beyond a size scale of a couple hundred, it becomes much more random. The black here is the same profile plot on a random graph with the same degree distribution. Notice we have a dip there. We'll get back to that, but ask, why do you see that dip? Where's ground truth? So these are million node graphs, and they're intractable. So how do you know what's going on? Maybe we were, and it's a fair question, maybe we were sloppy or just dumb or buried somewhere there's a cut down there, right? Or maybe spectrum, we'll get to that. So that's a random graph with the same degree distribution, and we have a bunch of different tools, and let me not get into blue, but this actually gets to this connected thing that you asked about. So there's a lot of differences here that I'm glossing over, but a lot of those are rationalizable in terms of where the field, where the data came from. So we go down, we hit a minimum, we go up. What's going on here? So let me define, before I get to the lower bound issues, let me define something called the whisker. You can define this a range of different ways, but for now let me define a whisker to be a maximal subgraph detached from the network by removing a single edge. So think of this as a 50 or 100 node clump that's connected by a single edge. And an empirical fact is that in almost every network, the minimum is a whisker. Now, what you want to say is, of course, that's a nuisance. Just cut them off. And if the data set sat on the plane and you had one 100-node clump here connected by an edge, you could do that and you wouldn't damage the overall structure. If you cut that whisker off, there's another whisker and another whisker. And the whiskers contain 40% of the nodes and 20% of the edges. So you can't be cutting them off. I'll show you what happens if you do cut them off in a second. But everyone knows what you're looking for if you go to Google and search on Britney Spears. Right? Or if you search on Yahoo at the Google search engine. And if you search on something that's never been entered before, there's not so much you can do. So it's exactly pushing the mass out down the heavy tail where all the revenue is. And so you can't be cutting that off. That's where all the action is. And let's define core to be the rest of the graph. So they're technically the two connected components, but we can define it in other ways. Global minimum is a whisker. And so what you see is that whiskers, these are the most easily visualizable ones since they're sort of small, but they're like the small things that you see very commonly in the literature. They have some sort of internal structure, and they might be clicks or might not, depending on the particular graph. So the lowest conductance point is a whisker. Say that if you remove all the whiskers, you're willing to eat that cost, cut off 40% of the nodes and 20% of the edges. What you see is the following. Red is what you saw before, and green is the core. So the core itself, and if you look at the minimum here, it's now a two-whisker. It's 100 nodes or 50 nodes connected by two edges, which makes sense, right? I mean, if you're 100 nodes connected by one edge, and you want to be the best conductance set, so with a set that has two edges, you're going to need a lot more edges inside this clump to make up for it. So the graph really has sort of a core periphery structure. There's sort of a core-like piece consisting of not the whiskers and all these little whiskers. But if you cut off all the whiskers, the core itself has a core-like structure, and it's a marginally more expander-like, but not much. So I think I have the lower bound. If not, let me mention that here, but I think I have that Yeah, so I'll get to your question in just a second. So what I plotted was a minimum. Let's look at the full ensemble that you get out of the randomization. So in a particular case, red is the flow-based method, METIS plus MQI. Blue is the ensemble of spectral methods. And we took what I showed you before is the minimum of this plot. So flow was better than spectral. The converse of that is the case in certain parts of the graph, but for here. And these are two different niceness measures. All right, two different niceness measures, meaning the diameter of the cluster. Maybe if you think it's a reasonable cluster community, the diameter should be a little bit smaller, not some convoluted thing. Or if you take it out and ask, what's the best cut inside that community? Is the community almost disconnected, or is the community pretty well connected? So these are two different niceness measures. And what you see is that the spectral methods are better than the flow-based methods. And so intuitively, the reason for that is that the spectral methods, because of the relationship to diffusion, will cut things off, and so you get slightly more compact sets. Whereas flow-based methods, I mean, think of it in terms of series and parallel circuits, if you're familiar with that. I mean, flow-based methods will consist maybe of two clusters that are barely connected by one or two edges here. So maybe they're not internally disconnected, although that heuristic that I skipped over a couple slides ago pastes together internally disconnected pieces, but they're sort of morally disconnected. And it's not clear at all how to enforce some niceness constraint. If you wanted to say something like it has to have small diameters or some other sort of thing that you might have in the back of your mind, which is a niceness measure, you're probably just define something intractable. And so you're going to have to approximate it with any of a range of heuristics. And so you're going to basically reduce to the things we're talking about now. What's the implicit geometric or statistical properties that the approximation algorithms will induce on the sets of nodes? So another nice thing about sitting on top of this machinery is that we can make very strong claims about things we can't find. How do we know that there was a set of nodes there and we were just too sloppy and couldn't find it? So spectral and flow-based methods sit on something called duality theory, so I don't want to get into the details of that. But duality allows you to get lower bounds, right? Any particular thing that we found is an upper bound. How do you know we didn't miss something? So spectral methods will give you you can use spectral techniques to get a lower bound on the cut of any size. So, there's not a cut anywhere in the graph lower than that. Maybe we missed something here or there, but there's nothing lower than that. And using SDP techniques, we can get bounds on cuts of equal volume, so 50-50. And so that's a lower bound, and that's a lower bound, and that's a lower bound. So what we're doing is developing tools to probe these graphs. And it's possible we missed something there or there or there, but we definitely didn't miss something there. So we really have shown that the graphs are expander-like at large size scales. This lower bound is well above the upper bounds here. So there's good cuts at small size scales. If we look at the details of what these cuts look like, we see that depending on if we pull them out with spectral or flow or other things like that, they look more or less nice in terms of what you might intuitively think of as our communities. And we're talking about all this stuff in terms of conductance, but you could, in principle, do it with other things, which we're thinking about, but I'm not going to talk about today. So what we see is that these graphs they're not expanders, they're not hot dogs or pancakes or something that's nice and low dimensional and visualizable. And so that's good. So now we have very strong statements about empirically what these things look like. There's lots and lots of generative models. So you want to say good. So one of these models is going to be right. So preferential attachment, copying models, we add edges to the neighbors of a seed node, hierarchical models, geometric preferential attachment, small worlds, we have some sort of underlying geometry and you add edges randomly, random sort of configuration models. So let's see how these things look. So again, look at the red. Preferential attachment is an expander. Right? You come in, you add two edges based on their degrees. You've just injected a massive, massive amount of randomness. And so it's going to be an expander everywhere. Copying models is a bunch of them. This is one particular one that a group at IBM developed about 10 years ago that fits probably the triangles closed. So when you're talking about clustering coefficients and triangles closing, the intuition you want to capture is that there's local clustering. And that's actually a discriminative statistic if you look at a lot of these networks. But if you try and fit any network to that, that's a much, much too local thing. Now the solution might be, why don't I go to 4 GONs and 5 GONs and 6 GONs and 50 GONs? But by then you have something that's totally intractable and you've overfit, I don't know what, overfitted, right? So what you're trying to capture here is these 50 node clusters, some sort of notion of clustering. But what you see is that you're marginally less expander-like, but not much. This is the Ravez-Barabasi hierarchical model. There's a bunch of others that behave in the same way. Even though there's not an underlying geometry explicitly in this model, the fact that you're connecting to first cousins or second cousins or third cousins with some probability means that there are good partitions of this thing into left half and right half. And these geometric models have an expander-like regime, and then the underlying low dimensional structure takes over. So what could be going on to explain these things? So what's the simplest possible model that might reproduce the observations of having deep cuts at small size scales. Right? We could be talking about communities, but you could just be talking about the structure of the graph, the geometric structure of the graph. What's the simplest possible model that might reproduce the properties of having deep cuts at small size scales and none at large size scales? So here's a theorem that says, let W be some power law vector, the Chung-Lu model, if you know what that is, and connect nodes I and j with a probability that depends on that power law vector. Then theorem, there's a deep cut, log depth of log size, and if you go a factor of 10 larger, there's no cuts in this regime, more than a constant factor deeper than the basal random level. So now you say, good, it's these darn power laws. You know, they're the root of all these problems. Exactly the same theorem holds for air de Cheney. All right, exactly the same theorem holds for air de Cheney. Now, air de Cheney has a parameter that says the probability that you've added links. And the vast majority of work has this probability larger than log n. So if you're at 1 over n, you have a giant component. If you're at log n over n, you're fully connected. You can imagine that by the time you get fully connected, you've put a lot of randomness in. So here, you're fully connected, but your measures started to concentrate, and you put a massive amount of randomness in. Here, you're not fully connected. So assume that at the data pre-processing step, you've thrown out all those little guys. Right? There's some little advertiser off and who knows where that you just thrown out because he's a small potato. And so what you have here is a core-like piece with a bunch of little things hanging off. And that's exactly what you're seeing. So really, it's air de Cheney. It's sparsity, very, very sparse air de Cheney, coupled with randomness is the issue, not the heavy tails. It's just that the heavy tails happen to give you that bad variability. But if measure doesn't concentrate for other reasons, it's exactly the same sort of thing. All right, and so this should tell you why the statistical properties implicit in the worst case algorithms actually reveal a lot of insight, because it's the sparsity that's causing us the problems. So there's a model that I'm going to skip over that can be sort of seen as a bit of an improvement of that. And let's talk about ground truth. So there's a lot of networks where you might have some notion of ground truth. And in this business, if you have a notion of ground truth that's sort of simple or clean, it's, again, probably wrong. So there's problems with each of these notions of ground truth. But let's look at them. So LiveJournal uses create and join online groups. So let's say those are ground truth clusters or communities. Co-authorship, publication venues. Amazon all product. Each item belongs to one or more hierarchically organized categories defined by Amazon. Actors to movies. Countries and production and languages may be viewed as clusters. Now you might say, oh, you know, I publish in a lot of places, so things might overlap. So, you know, that's maybe the semantics here over the edges are sort of weak, as opposed to actors to movies where you sort of roughly have to learn a language to be in that movie. You hope that the marketers at Amazon might do better than the random level. I mean, that's an empirical question, of course. So so now let's look at a profile plot for these ground truth clusters. The red is what we saw before. The black is the random basal level. And the green on LiveJournal, and this is typical of these very social thing, goes down, hits a minimum at 50 or 100, and goes up and basically is indistinguishable from the random basal level. Co-authorship, you go down, maybe you're a little bit below, but basically you hit back to the random basal level, maybe because the communities overlap in different conferences. The hierarchy that Amazon gives even goes down and hits a minimum and goes back up. Of course, you're above the red because we optimized the y-axis in the red, but you're well below the random basal level. But, you know, so there's structure, but the structure's on a basal level, you know, basal background of noise. And the actors to movie, the same thing, although this is the smallest one of the four and so it's much noisier. So this has all been sort of technical, and except for maybe the last little piece in terms of how it might map. So we've thought about a number of different things, just to give you a sense. So there's been sociological work on clustering and community size. So something Dunbar did some work on a bunch of different species, and he correlated the size of clusters or communities with something in the back of the brain, the neonatal cortex or something. And roughly the question is, if you're going to have a set of clusterings, you know, I need to not only model my interaction with you, but I need to model the way, you know, you're interacting with all these different people. And so, you know, I think it was 147.3 or something, but ballpark 100 is a maximum cluster size. And a range of online work has shown the same sort of thing. So if you're in an army division, your head's on the chopping block, you might go to a little bit more effort to get up to that high. But if you're in an online community where the barrier to entry and exit is much less, it might be a little bit lower, and 60 and 80 have been seen in those settings. Common bond versus common identity theory. So we're talking about clusters in terms of what people, when they write papers, say this is what I think a community is, internal versus external. But in some clusters, people might be attached to the individual community members. You join the bridge club because your friends are there, not because you particularly care about bridge, but you join each week to see your friends. Common identity, people are attached to the group as a whole. So in the U.S., there's something called the NRA, which is an organization that likes to have guns and that sort of thing. And so even if you don't particularly know anyone in the organization, you might really believe that this is a good thing, and so you stay in that group. And so the relationship that you might have to other members of that group would be presumably very different in these sorts of two cases. So we had some results, but a little ambiguous, but it would be interesting to speculate the different sorts of clusters that you'd see in different parts of the graphs. And as we saw, what the edges mean in terms of semantics over the edges and the different types of graphs in terms of community identification. So social networks, people add links for all sorts of reasons. Citation graphs maybe in some sense are more expansive, and so there's a little bit more semantic uniformity. So let me wrap up. This is a little bit some other things, sort of a more technical variety. Let me sort of skip. And before the conclusion side, so the really, a lot of stuff's done on latent semantic indexing and so on in a range of these sorts of techniques. If you have a heavy tail over degrees and any amount of randomness, you can have a heavy tail over eigenvalues. So it's not the case that any sort of linear global geometric techniques will be particularly appropriate for capturing the data. Not particularly nice manifolds that describe the data well. There is sort of locally linear structure, and if you're in machine learning, that's sort of a very loaded term. But it's useful maybe to think of sort of local dictionaries or local subspaces that might be useful in some sense. So locally linear structure or local structure that's sort of meaningfully or operationally geometric. On small size scales, 100. Maybe at a size scale 1,000, but in a sense it's worse than 100 or 10,000 or so on. It gets worse and worse. That structure doesn't propagate in nice ways to global size scales. So you see that things are empirically, they're expander-like, and we have lower bounds. So they're definitely expander-like at large size scales. So at large size scales, the true underlying geometry, it's expander-like, but there's a very significant degree of heterogeneity here. So you're enhancing something called hyperbolicity. And so hyperbolicity means you're going to be a little bit more tree-like, but not tree-like in just a binary sense, but because the hierarchical models have that, but tree-like in a certain core periphery sense. And it's unfortunate because this is important that it's cut off. But even if you do not care about communities, conductance or whatever, well, I'll have to skip that. These empirical observations place very severe constraints on the sorts of models that might be appropriate, on the sorts of tools that might be appropriate, right? If you're going to do some recursive bisection, it matters whether you're nibbling off 100 nodes out of 1,000,000, because then the recursion depth is going to be very, very, very deep. There's implicit size constraints if you just sort of posit an objective function. The objective functions oftentimes have very non-obvious behavior as a function of size. So even if you don't particularly care about clusters or communities, these empirical observations place very severe constraints on the types of models, statistical models that might be appropriate. And in particular, you're never going to get measured at concentrates. So you need to be looking at sort of pockets of structures on top of sort of empirical quasi-randomness. So you can think about machine learning issues on some of these graphs, but let me skip over that. Except to say that machine learning usually makes sort of niceness assumptions, and so doing machine learning when you're in these sorts of more heterogeneous environments is a little bit tricky. So with that, let me wrap up. We used approximation algorithms as experimental probes, so there's a lot of technical issues that I glossed over in terms of how these algorithms behave, but hopefully I gave you a little bit of sort of an intuitive sense for how these things might behave. You have a hard-to-cut onion-like core with a lot more structure than random. Every graph was well below the random Besa level, but the small sort of isolated clusters gradually blend into the core. You might say, what about overlapping communities? What about a lot of things? And that is in some sense overloading the term community. That's actually a very reasonable thing to think about, maybe clustering edges, because people add edges for different reasons. But then you're just dealing with something that's very different than this internal versus external bicriterion, which is maybe the intuitive motivation. But that's actually, for reasons I didn't get into, something that is actually pretty promising. Common generative models don't capture the community phenomenon even qualitatively, and if you don't want to use community there, just say the geometric structure, right? You have things locally where there's some sort of Euclidean geometry that you can look at and think about. At larger size scales, things are much more hyperbolic or tree-like, and so the way the local properties of the graph will interact with the global properties, the way local diffusions will interact with the global structure, etc., will be very, very different. And the implicit statistical regularization that we did inside the approximation algorithms, right? We didn't tack on an extra regularization term, because now you just get another intractable problem. We did it inside the approximation algorithms because the implicit geometry there, it was actually critical for the use of these tools. So with that, let me wrap up, and thank you for your attention.
So I'm a little bit puzzled by your notion of ground truth. So I thought, like, I understood ground truth to be, let's take LiveJournal, and you really have every node and every link at time t. That's my ground truth. And
Okay.
you don't have that ground truth for sure.
So ground truth means, okay, so there's the issue about aggregating the graphs. So you do it over 1 year or something, which is basically the procedure you said. And then ground truth is there's a self-declared, you say I want to belong to this group.
Yeah.
And so look at people who belonged in that group at some point during that year.
But I mean, there is this ground truth of having that 1 year, well, whatever time slot you think, that ground truth sitting in front of you. Take the AS graph. You don't have the ground truth in the sense that you do not have the graph.
Right.
So what do you compare with?
Yeah, so what do you do? I don't know. I mean, so a lot of these graphs are grown with sort of a mechanism that might be analogous to the way the ground truth AS graph is sort of found. You do some you go to sort of nearest neighbors or something. I mean, I don't know with respect to things like the autonomous systems how that would be, but these sorts of things, a lot of them are generated that way, and in a sense, if you give people a factor of 10 more time, I mean, I don't know what the ground truth LiveJournal graph, I mean, I think it's sort of a meaningless thing to ask for. I mean, clearly, in principle, one could look at the entire autonomous system, but for any of these other ones, the way they're sort of generated, if you allowed a factor of 10 more time or a factor of 10 more people on or a factor of 10 more edges or a factor of 10 more anything, it's not like you'd flesh out the same structures. People would link for different reasons, people would do different things, and you'd still see the same sort of local to global properties.
But I'm more concerned of in the AS case, for example, we know exactly what types of links you do not have in your
Right.
and they are there. So what does
So I don't know.
what does that absence of critical links mean for many of these algorithms?
Yeah, so the AS graph is exceptional here because you don't have the little clusters in some sense. I mean, roughly, you do actually have a little bit, but you don't roughly. So what I suspect, and I don't know this for sure, but I suspect you'd see similar sorts of things, but obviously it would be modified because you'd have these extra edges for some reason. But in terms of the local to global structure, it may not be so different just because we've seen this in a lot of different cases. But this particular engineered graph is actually one of the more exceptional ones. So we should talk a little bit more offline because I don't know the answer to that.
I'm going to suggest that you talk about it over the break.
Yeah.
So thanks again, Michael.
All right.